introduce the first question, and it is Stephen Wheeler, and he will talk about Schreier multisets and the estate Fibonacci subsector.
So thank you very much for the invitation. I apologize if it is hard to hear me, not because of the Boston accent, but because I have had 2 dental surgeries in the past week. And so I'm actually a little bit happy that we lost some time with technology issues, so I don't have to talk for quite as long right now. So anything I don't get to, it's in the slides, so just please email me. This is joint work I did with students as part of the polymath program. And so if you haven't heard of that before, I've got a link to that on the main page. I'm happy to chat more about this. We take students all over the world as long as they've had 1 theoretical class. So this is joint work with some undergraduates supervised by a former REU student of mine who was then a graduate student at the time. Amazingly, when we did all the technology stuff, it's now working and it is mirroring both screens, so it did work out in the end. All right, so what I want to do is talk a little bit about Schreier sets in the Fibonacci sequence. I am very thankful to the organizers for having the previous talk introduce a lot of the notation that I'm going to be using. This is a talk that could have been done in either the Fibonacci conference or integers. It's also nice that these 2 conferences are different mod 2. Okay, so we say a set is Schreier if the smallest element in the set, which we'll denote by minimum of A, is greater than or equal to the number of elements in the set. So for example, the set 2, 3, 2, 4, 2, 5, these would all be Schreier. And you can see that any set with 2 elements where the smallest element is 2 would work. 4, 5, 20 would work, a lot of other things like that. 2, 5, 6 would not. The smallest element is 2, but there are 3 elements in the set. So we want to come up with a nice way to look at sets without loss of generality. Let's divide them based on what is the largest element in the set. So I'll put a subscript n to denote that I want the largest element in my set to be n. So the 2, 3, 2, 4, 2, 5, they would all be examples, but they would be put in different bins. And so we want to try to count how many Schreier sets are there where their largest element is n. And so how do we count this? Well, it turns out that by just brute force calculations, you see very quickly that the number is 1, 1, 2, 3, 5. When you see a pattern like this, it is very natural to conjecture that this is going to be the Fibonacci sequence. And Bird did show that back in, I think, 2012. And so we'll follow the method of proof that he gave. It's a really nice, straightforward. And as soon as you see the relationship like this, it suggests that there should be a way to split your Schreier sets into 2 subsets, depending on properties, where one set will have cardinality Fn-1 and the other will have cardinality Fn-2. Okay, so the way we're going to do it is, without loss of generality, we handle the base case, and then we want to show that the number of elements in an plus 2, where n plus 2 is your largest number, is equal to the number of elements in n plus 1 and the number of elements in n. And we're going to consider the following 2 maps. So for the first map, we take anything that's a Schreier set where n plus 1 is the largest element, and we just replace n plus 1 with n plus 2. And for the second, what we're going to do is we're going to just add 1 to each element, and then we're going to append n plus 2. So with a little bit of work, you can see that both of these maps are 1-to-1. And with a little bit more work, if you just look and see what happens, well, the first one is shifting things in n plus 1 to n plus 2, and they're not going to have the element n plus 1, because we replaced the largest element with n plus 2. In the second one, we're going to have n plus 2 as our largest element, and we're going to have n plus 1. So these 2 sets are distinct. And then if you just think about it a little bit more, you can see that this will get every single possible element. If I have a Schreier set where the largest element is n plus 2, if it doesn't have n plus 1, then it's basically coming from over here. If I have n plus 2 and n plus 1, if I remove n plus 2 and then shift everything down, I've decreased the number of elements in my set. I know I didn't initially have the element 1 if I have n plus 1 and n plus 2, because if I have n plus 1 and n plus 2, my set has at least 2 elements, so I can't have 1 as the smallest element in my set. All right, so we can then ask, we have this nice connection between the cardinality of these Schreier sets and the Fibonacci numbers. Do we have other equivalences between related sets and sequences related to the Fibonacci numbers? So unfortunately, I did not look at the abstracts closely, so I'm using S, and the previous talk I think used K for looking at the sequence. Just do a search and replace from the last talk. And so the S-step Fibonacci sequence will be you are the sum of the S previous terms. And so we'll initialize a couple of things to be 0 and then 1, and then use the recurrence relation to fill in everything from that point onward. And so if we just take s equals 2, we get the standard Fibonacci sequence. If we take s equals 3, we get the Fibonacci sequence. And so our problem is to show how can we generate the k-step Fibonacci sequence by some kind of Schreier-like condition. Is there some kind of equivalence like we saw before? And the answer is there is a way to do this. Rather than using sets, all we have to do is use multisets. Like almost every problem in combinatorics, a lot of it is going to come down to how do you choose to define things. And so the definition might be a little bit strange at first in terms of how we count things. Don't worry, we will not be consistent with notation throughout, so that if you don't like this definition, there'll be a related one that will come into play very, very shortly afterwards. All right, so we'll talk about how do we use multisets to do this. So a multiset is going to be a collection where you can have multiple copies of the same element. So we will say that a multiset is Schreier if the smallest element in the multiset is at least as large as the cardinality of the set. So for example, 4, 5, 5 would be considered Schreier right now, and 5, 6, 6, 10, 12 would be, but 2, 3, 3 would not. Later on, we'll see that it's a little bit bad to count with having 2 copies of the largest element. And so it's a little bit easier to split things up so that we only have one largest of that. So again, further avenues to pursue. If you change the definition slightly, how does that impact the relationships you get? So we're going to define our sets as follows. So we're going to allow yourself to have up to s-1 copies of 1, up to s-1 copies of 2, and so on and so on and so on. But you can only have 1 copy of the largest element. And this is going to lead to a really nice split, because once I choose my largest element, I can't go back and take anything else from that bin. All of my other choices have to be from the smaller bins. And so if we consider s to be greater than 2, the s-step Fibonacci sequence defined as follows, with a recurrence relation as we've seen before. And what we were able to show is that the cardinality of an s-1 is just equal to the terms in the sequence. It's a really nice generalization of the Fibonacci relationship. The proof is actually very straightforward if you're familiar with the literature in terms of what results are out there on counting multisets. So fortunately for me, I can actually look at the screen because my eyesight is failing and it's tough for me to just see on the slides of the iPad. So if we put a subscript s, this modifies the binomial coefficient to mean it's the number of ways I can distribute k identical objects among n labeled boxes, where each box gets at most s elements. So the standard binomial coefficient would just be the case when s equals 1. And so s equals 1 is the classical case. And then we have the following well-known identity, where if I sum these binomial coefficients along this diagonal of Pascal's triangle, I get the Fibonacci numbers. And this generalizes immediately to counting where you're allowed some repetitions. And so the generalization is just if you sum these modified binomial coefficients, you get these related Fibonacci numbers. And that's going to essentially be all we need to prove our result. So trivially, if I just consider the element that has only n, this is going to be in our generalization of the n-Schreier set. And so now what we want to do is we want to look at all the different ways we can add k elements, such that we choose at most s-1 in each of these various bins. And so another way of looking at this is we want to put k elements into the boxes labeled k plus 1, k plus 2, all the way up to n minus 1. And then by definition, there's n minus 1 minus k, choose k, sub s-1 ways to do this. So we've just got to be a little bit careful. Obviously, if I want to have one element, I've already got the element n in my set, so I can't choose anything else. If I want to have exactly 2 elements, then I can choose one more element. And I've got some constraints on Schreier. So one of the best pieces of advice I ever got when I was young was never do algebra in public, especially when it's being recorded. So the goal here is to just give you a rough sense of this is how you would do the counting if you really wanted to do the counting. You don't want to see me do the counting in public, and so I'm not going to do the counting in public. And just if you go through and just trace through all of the definitions, this is what you get at the end of the day. And so when you look at it, you just have to play some games to see what's the largest value k can go to? You know, I can clearly add no elements because just the set containing n is Schreier. What's the maximum I can do? You go through, you do the inequalities, and you get a result. Okay. So I think I've got about 4 minutes left because I am going to get the conference back on schedule. Yes. And so there are other ways and other related problems you can do to get sequences like this. And so another one is, let's consider a sequence of integers Sn such that Sn is greater than or equal to k for all n at least 2k plus 1. And then what I want to do now is I want to modify what might have been an unnatural definition to some of you, where I was having the last one could only have one element. Let's say I can choose S11s, S22s, all the way up to at most SNNs. What kind of sequence would I get if I do something like this? Well, to some extent, I can just increase the S's and it's not going to really make much of a difference. I can't have more than 1 because my minimum element has to be greater than or equal to the cardinality. If I had 16 ones available, it doesn't matter. I can only have one of them in my set. So even though I have conditions like this, you can talk about the minimal sequence that would have this as its property. And not surprisingly, it turns out that if you go through and you count, how many sets do I have like this? There's a really nice correspondence as well. And you get a very similar result in terms of these Fibonacci numbers and then these generalized Fibonacci numbers. So in particular, if anybody has good notation for this, we called them Skipinacci numbers years ago because you skip a couple of things. And then I think they might have become kangaroo numbers when you have multiple hops and you skip multiple times. So in homage to where different people hailed from. So again, if u equals 2, then this is going to reduce to the standard Fibonacci's, but it allows you to have a little bit of a gap. And when you go through and you start playing the same counting games as before, when the dust settles, you get a very similar result in terms of there is a nice correspondence and the number of such elements is related beautifully to a recurrence relation. One of the things I'm always interested in is going back and forth between recurrence relations and combinatorics. I've done a lot of stuff on Zeckendorf's theorem, writing integers as sums of non-adjacents. There's a unique decomposition. You can ask what other recurrence relations have unique decompositions and whatnot. And so there's a lot of related questions to this that you can do. I will just end very, very quickly with one last one, a nonlinear condition, which is going to reduce, not surprisingly, if you choose the parameters appropriately, to what we've already been looking at. So we're going to now look at a set where the minimum element is greater than or equal to something raised to the pth power. So what do I mean here? So I want to count the number of decompositions of n where the smallest part is greater than the number of parts raised to the pth power. And so if we just take p equals 0, then that would just be counting the number of elements. And so it should just reduce back to the Fibonacci's. And not surprisingly, when the dust settles, we end up getting a very similar relationship where we again have nice formulas to count objects like this. So just very, very briefly in terms of future research questions that one can do. You can start putting in different weights in terms of all these different types of relationships. It's at the end of the day, can you come up with very natural conditions that are equivalent to natural counting problems? So if anybody is interested in pursuing any of this, if anybody has graduate students who are interested in pursuing questions like this, we have, as I said, the Polymath RU program. It is entirely remote. People can do it all over the world. If you have students who are not US students, doesn't matter at all. We take anybody who's had, for the most part, one research class. And so while it's too late for undergraduates to join this year, if you have some graduate students who would like to assist and help mentor problems like this, please let me know. So thank you.